This video is going to cover chapter 6, sections 1, 2, and 3. So we start, as usual, with some definitions. We start with the definition of perpendicular and angle bisectors. So the perpendicular bisector definition is a segment, ray, line, or plane that's perpendicular to a segment at its midpoint. So there's obviously two parts to this word, perpendicular, or to the name, and bisector. Perpendicular is where the right angle has to come from, and then bisector, if a segment is bisected, it's cut into two congruent parts. So this thing does both of that. A reminder that the word equidistant, so that's going to appear in the theorems in this section, means the same distance. The perpendicular bisector theorem says in a plane, if a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segment. So if we're looking at a diagram, it usually will look something like this, where you have your segment that's being bisected. You know it's bisected because it's cut into two congruent pieces. And if it's the perpendicular bisector, then it means it's got that right angle. So when that happens, any point along that bisector, in this case we were talking about point C, would be equidistant from the end points of that bisector. So in this case, from C to A would equal the distance from C to B. So we can either say if CP, line CP, is the bisector of segment AB, then CA equals CB, or you can say C is equidistant from the endpoints of AB. Same thing. The converse to the perpendicular bisector theorem, switch the if and the then. It says in a plane, if a point is equidistant from the endpoints of a segment, then it's on the perpendicular bisector of the segment. So in this case, if you've got a point, so for example, we're looking at point D this time, is equidistant from the endpoints of the segment. So because these are marked as congruent, we would know that that's equidistant from the endpoints. Then it's determined that D lies on the perpendicular bisector of AB. So in this case, if DA equals DB, then point D lies on the perpendicular bisector of AB. Okay, so in these examples, we'll figure out how we can use this information. So example 1 says BD is the perpendicular bisector of AC. Find AD. So if BD is the perpendicular bisector of AC, then this is a right angle. These are congruent, and any point on that bisector, for example, D, would be equidistant from the endpoints of the segment, which means 3x plus 14 would equal 5x. I would subtract the 3x, and 14 equals 2x, divide by 2, and x is 7. It wants the measure of AD, so I'm going to take 7 and plug it back in. And it wouldn't matter which one we plugged it back into because they should be congruent. But that one's definitely the simpler one to plug it back into anyways. So we're going to do that. 5 times 7 is 35. And the length of AD is 35. Example 2 says to use the diagram and the given information to find the indicated measure. So in number 1, it says ZX is the perpendicular bisector of WY. That again means these are congruent, and you already have the perpendicular part there. It says YZ is 13.75, and it wants you to find WZ. Z would be equidistant from the endpoint, so WZ is also 13.75. 2 says ZX is the perpendicular bisector of YWY, so same thing there. WZ is 4n minus 13, and YZ is n plus 17. So those two are equal. 4n minus 13 would equal n plus 17. Subtract the n. 3n minus 13 is equal to 17. Add the 13. 3n equals 30. Divide by 3. And n is 10. It wants YZ. So we're going to plug it back in. 10 plus 17 is 27. clear this off so we can go to the next one. The next one says, find WX when WZ is 20.5, WY is 14.8, and YZ is 20.5. So this time it didn't give you the piece of information about it being the perpendicular bisector. But because these are equal in distance, I know Z lies on the perpendicular bisector of WY, which means it cuts it into two congruent pieces. And WX would be 1/2 that 14.8, or 7.4. Okay, the next theorem focuses on an angle bisector. So we know by definition an angle bisector is a segment line, is a ray segment or line that cuts an angle into two congruent parts. So the theorem says if a point is on the bisector of the angle, then it's equidistant from the two sides of the angle. So in this diagram, you've got your full angle and then AD, which is bisecting that angle. We know it bisects because of a couple things. 1, you'll see the congruency marks here. 2, you would see measures being equal there. 3, it will literally say if AD bisects angle BAC. If that happens, then the points that are equidistant from any point on your angle bisector will show this way. So they have to have this right angle mark because that's what shows the true distance. And it would be from any point on that angle bisector. If that's true, then those little segments are congruent. So if I had a point, let's say here, and I called it E, then from E to the perpendicular distance of AC, and then E on the other side, perpendicular distance, would also be congruent. You have to have the right angles to show the true distance. And just like with the perpendicular bisector, you have the converse to the angle bisector theorem. And it says if a point's on the interior of an angle and is equidistant from the sides of the angle, then it lies on the bisector of the angle. So in this case, you've got point D. From D to B is marked as congruent with the right angle. So I know D is equidistant from the sides of the angle. And if that's the case, then we know AD is the bisector of that angle. So example 3 says, find the value of X. In each of these diagrams, if I look at just A first, so I've got the angle bisector, and I know it's true because these are both 27. And if it bisects that angle, then it is equidistant from the sides of that angle. These right angles show me that this is congruent to this, so X equals 15. B is the reverse. It's showing you that this segment is equidistant from the sides. If it's equidistant from the sides, then it bisects this angle, and so 3x plus 5 would equal 4x minus 6. I know it's hard to read, but that's a 6. So I would subtract the 3x. 5 equals x minus 6, and add the 6, and x is 11. So A was the original theorem, and B was the converse. C is also showing the angle bisector. So this is the original one that says that these segments would be congruent. 5x would equal 6x minus 5. Subtract the 6x. Negative x would equal negative 5. And x would equal 5. All right, example 4 says, write the equation of the perpendicular bisector of the segment with endpoints P, -2, 3, and Q, 4, 1. So I'm going to go ahead and plot that on my graph. -2, 3 is P, and 4, 1 is Q. So that's the segment that's being bisected. So the first thing I want to do is find the midpoint of that, because then I know that that's a point it crosses through. So the midpoint, I'm going to add the 2 x's, divide by 2, add the 2 y's, divide by 2. I get 2 over 2, 4 over 2, 1, 2. So that's a point that the perpendicular bisector crosses through. That's going to help me find the equation of the line. And then to find the slope of the line, I know these are perpendicular. So I need to find the slope of PQ and then find the opposite reciprocal. So the slope of PQ would be 1 minus 3, 4 minus a negative 2 becomes plus 2. Negative 2 over 6, which is negative 1/3. That's the slope of PQ. To find the slope of a perpendicular to PQ would be positive 3. So this is my M, this is my point, and I'm going to plug it into point slope. Y minus y1 equals M times x minus x1. Y minus 2 equals M times x minus 1. Y minus 2 equals 3x minus 3, and add the 2. And y equals 3x minus 1. Now you can always check if that lines up. Here my y-intercept looks like it was negative 1, up 1, 2, 3 over 1, and there is my equation of the line that's perpendicular to the segment and bisects it. All right, chapter 6, section 2 is called bisectors of triangles. So now we take it into a couple new segments and figure out what happens when they are inside your triangle. First definition is called concurrent lines, and concurrent lines are 3 or more lines, rays, or segments that intersect in the same point. So any 3 lines that intersect at the same point, these would all be called concurrent lines. The point of concurrency is the point of intersection of those lines, rays, or segments. The circumcenter is the point of concurrency of 3 perpendicular bisectors of a triangle. So each side of the triangle has a perpendicular bisector. If we look at this first one, so the block is obviously the triangle. If I were to measure and find the perpendicular bisector of each side, this would be in 2 parts. This would be my right angle, and this would be my perpendicular bisector. I could rotate around. This would be my right angle. This would be 2 congruent parts. This would be the perpendicular bisector. And on the other side, center and perpendicular. So this would be its perpendicular bisector. And they will always meet. In an acute triangle, they meet inside the triangle. On a right triangle, they meet on the triangle. And on an obtuse triangle, they meet outside the triangle. So you would actually, if I had just drawn my perpendicular bisectors here, they wouldn't intersect. I'd have to extend them beyond the circle or beyond the triangle, and then they would intersect at that point of concurrency. And again, that point of concurrency is called the circumcenter. We're going to have a lot of these names for concurrent points within all these different types of segments. So remember that circumcenter goes with perpendicular bisector. And they meet 3 different locations: in, on, and outside the triangle, because that's another thing that you're going to get tested on. The wording on this second one just says the circle with center P is said to be circumscribed about that triangle. So the circle is the wording on that is circumscribed about the triangle. If the circle was inside the triangle, we say it's inscribed inside the triangle. All right, the circumcenter theorem says the circumcenter of a triangle is equidistant from the vertices of the triangle, or the point where the 3 perpendicular bisectors meet is equidistant from the vertices. So in this diagram, the perpendicular bisectors would be the blue lines, and I would know that because they are at the midpoint of each side, and they are perpendicular. So it would either tell you that those are the perpendicular bisectors, or it would tell you P is the circumcenter, or all that information I just marked would be marked. And based on that, you can determine that from that point to each vertex, so from P to B and P to A and P to C are all congruent. So in this diagram, PA would equal PB would equal PC. Example 1 says find the coordinates of the circumcenter of AB with vertices 0, 3, 0, -1, and 6, -1. So if this is my circle, if this is my triangle, then I would find the perpendicular bisector of each side. First of all, I'd find the midpoint, and I'd find my perpendicular segment. So on the legs of this right triangle, it should be easy because the perpendicular is going to either be vertical, or in this case, it would be here, and it would be horizontal. On the hypotenuse, the center of, or the midpoint of the hypotenuse would be found by finding the midpoint. So the long way around this is finding the midpoint from A to C. So I use these two. 0 plus 6 over 2, 3 plus a -1 over 2, 6 over 2, 2 over 2, which is 3, 1. If you graph it accurately, you'll find that that coordinate point is already where those other two segments meet. So those three and the perpendicular bisector would just run perpendicular to this. So those three, because this is a right triangle, meet at the midpoint of the hypotenuse. And that will happen for every right triangle. And the coordinates there is 3, 1. All right, now we're going to talk about the in-center. And the in-center is the point of concurrency of the angle bisectors. So circumcenter, perpendicular bisector, in-center, angle bisectors. This time it always lies inside the triangle. So it doesn't matter if your triangle is acute, obtuse, or right. It's always inside the triangle. This time the circle is inscribed within, not within, within the triangle. So the red segments would be my angle bisectors. I know that because those congruency marks marked on the angles, and they would again always meet inside the triangle. Just like with the perpendicular bisectors, there's a theorem that goes along with this, and it's called the in-center theorem. And it says the in-center of the triangle is equidistant from the sides of the triangle. So this time, my angle bisectors, which are in the red here, and I know that because they come from the angles, and it said it in the initial description, the angle bisectors, or they would be marked like this. These meet at a point that's called the in-center, so P is the in-center. And from the in-center to the sides, so you have to have the right angle marks there, are all congruent. So in this diagram, PD equals PE equals PF. Example 2 says in the figure shown, ND is equal to 5x minus 1 and NE is equal to 2x plus 11. So in this diagram, first thing you want to figure out is what kind of segments you're looking at. So those red lines all have congruency marks on the angles, which means the red lines are your angle bisectors. So this is angle bisectors. N would be the in-center. N from N to D, N to E, and N to G would all be, and N to F would all be congruent because of all the ones that have the right angle marks. So ND, which is this segment here, is 5x minus 1. And NE, which is this segment here, is 2x plus 11. Since those are both segments that go from the in-center to the side, they're congruent. So 5x minus 1 would equal 2x plus 11. Subtract the 2x. 3x minus 1 would equal 11. Add the 1. 3x would equal 12. Divide by 3. And x is 4. So NF is the same length as those other two. I could take that 4 and I could plug it back into either of them. So if I plug it back into the 5 times x minus 1, I'd get 20 minus 1, which is 19. And it would be the same if I plugged it into NE and the same length for NF. So this one is 19. B says, can NG be equal to 18? So if I look at this diagram, NG is not the right angle, so it's not the shortest distance. It would be opposite the largest angle when that right angle, which means it has to be longer than this segment here. We just said this segment here was 19. So it is not possible for it to equal 18. It must be larger than 19. And it could be because it's opposite the right angle. It could be because it's the hypotenuse of that triangle, something like that. All right, chapter 6, section 3 is now medians and altitudes. So when we're done with this, we've covered perpendicular bisectors, angle bisectors, medians, and altitudes. The median of a triangle is the segment from the vertex to the midpoint of the opposite side. So if this is my triangle, I would find the midpoint of one of the sides. In this case, we're doing this one, find the midpoint here, and connect it to the opposite vertex. That segment is called the median. If I do it on the other two, if I could just like eyeball center here, it'd be about there, and then connect it to the opposite vertex, that would be a median, and then repeat it over here. It appears about that's the center, and connect it to its vertex, and it would be about there. Every triangle has 3 medians, just like the others, and the medians are concurrent, just like the others. The centroid is that point of concurrency. So circumcenter, perpendicular bisectors, incenter, angle bisectors, centroid, medians. This time, just like your incenter, it is always inside. So the perpendicular bisectors are the only ones that meet in, on, out so far. The centroid is also called the center of gravity because it's the point where a triangular region would balance. So if you had a triangular shaped object and you wanted to know how to perfectly balance it, you could find the centroid, or the point where the medians meet. The centroid theorem, so just like in-center theorem, circumcenter theorem, there's one for centroid, and it says the centroid of the triangle is 2/3 the distance from each vertex to the midpoint of the opposite side. So in this diagram, you'll see the 3 medians drawn. Again, I know they're medians because they go midpoint to vertex, midpoint to vertex, midpoint to vertex. And the theorem says that let's say, for example, this vertical one, from P to F would be 1/3 the length of this full segment, which is BF. This would be 2/3. So from vertex to centroid, 2/3. From centroid to side, 1/3. Same thing would happen on all the other ones. From vertex to centroid would be the 2/3. From centroid to the side would be 1/3. And other way as well, C to D would be 2/3, and P to D would be 1/3, the length of that whole median. All right, so example 1 here says, in triangle LMN, S is the centroid. Again, I have to know centroid means median, and that's my 2/3 one. If RL, which is this whole segment here, is 21, and SQ is 4, it wants you to find LS and NQ. So LS is the segment that covers from the vertex to the centroid, which means it's 2/3 the length of 21. 21 times 2/3 would be 14. So you can either divide 21 by 3 and then multiply by 2, or you can simplify it the way we just did it. And then NQ is the full median here, and you have the 1/3 part. So if that's 1/3, then I double it to get the 2/3 part, multiply or and add those together and get 12, or take your 4 and multiply it times 3. Either way, you'd get NQ is 12. Example 2 says a sculptor is shaping a triangular piece of iron that will balance on the point of a cone. At what coordinates will the triangular region balance? So we want to find the median or the centroid of this triangle. To do that, we're going to find where the medians meet. So I have to find the midpoint of each side and then draw where they meet. So if I start with the midpoint on this side, let's say, I would do 6 plus 8 divided by 2 and 6 plus 2 divided by 2. 14 divided by 2, which is 7. And 8 divided by 2, which is 4. So 7, 4 is here. That would be one median. Find the midpoint of another one. So I could find the midpoint of these two. 6 plus 10 over 2 and 6 plus 7 over 2. 16 over 2, which is 8. And 13 over 2, which is 6.5. 8 and 6.5 is here. Connect those. And I can already tell where they're going to meet, but if I needed to confirm it with the last one, I would find the midpoint over here with these two, 10, 7, and 8, 2. 10 plus 8 over 2, 7 plus 2 over 2, 18 over 2, which is 9, and 9 over 2, which is 4.5. 9 and 4.5 is that point there, and connect it. And that coordinate point is 8, 5. Now there is a shortcut to this. And it is you add the 3 x's, divide by 3, add the 3 y's, and divide by 3. So I would do 6 plus 10 plus 8 over 3, and 6 plus 7 plus 2 over 3. This is 16 plus 8, 24 over 3, and that's 8. 13 plus 2, 15 over 3, which is 5. So the shortcut is obviously way faster, but if you forget it, you could always find it the way we did the first way. But the shortcut, and this only works for the medians, so that it only works for the centroids. You just add them all up, divide by 3. All right, the last of the special segments is called the altitude. And the altitude of the triangle is the perpendicular segment from the vertex to the line containing the opposite side. Every triangle has 3 altitudes. And like your perpendicular bisectors, the altitudes can be in, on, or outside the triangle. So what's unique about an altitude is that it actually doesn't have to go inside your triangle at all. In an acute triangle like the one on the left, the altitude goes from the vertex and it's perpendicular to the other side. But in an obtuse triangle, if I tried to go from the vertex, let's say I try to go from Q to the opposite side and I try to stay inside that triangle, nowhere am I going to get that right angle. I have to swing this outside the triangle and I'd have to extend the side of the triangle out in order to obtain that right angle. The same thing would happen on the other acute angle, this R. If I went this way, I couldn't get a right angle until I swing it outside, and I'd have to extend this side out, which is why these angles, so this one works, the P, I can go from P to the other side and I can make my right angle. But those 3 don't meet unless I extend P the other direction, and then I can get these 3 to meet outside the triangle. So just like before, it's going to happen in, on, and out. On the acute triangle, it's going to be in. On the right triangle, it's going to be on. And on the obtuse triangle, it's going to be outside. This point is called the orthocenter. So circumcenters, perpendicular bisectors. Incenters is angle bisectors. Centroid is medians. Orthocenters are altitudes. The lines containing the altitudes are concurrent. The point of concurrency is the orthocenter. And the lines containing these, like if you look in this triangle, this is an acute triangle. So here are your altitudes, and they all meet at the point G, which would be the orthocenter of the triangle. The good news about altitudes is there's no other theorem you have to learn. You just have to know that they meet, and you have to know that it's in, on, out. Example 3 says to find the orthocenter of x, y, z, where x is -3, -4. Y is -3, +4. And z is 5, 4. So this is, again, a right triangle, just like that last example that we did with the perpendicular bisectors. So the perpendicular sides all double as altitudes for the legs. So the altitude is going to be here from x to z, from here to y to z. The only other one we have to find is the one that goes from y to the opposite side at a right angle. But using the other two legs, we already know where they meet, which means this coordinate point, the coordinate point of your right angle, is going to be the orthocenter. And that coordinate point is -3, 4. So the orthocenter not only occurs on the right triangle, but specifically at the right angle. All right, the location of the orthocenter. So here's what it looks like when you break it down into your acute, right, and obtuse triangles. On the left is your acute one, which we already saw. They would meet inside the triangle. In the middle one, this is the right triangle. It's going to meet at the right angle. So it's going to meet on the triangle. And the last one, the black is your triangle. The reds are your altitudes, and they will meet outside the triangle. So in, on, out, just like the circumcenters. All right, this is all four on the same slide. So this is a really important slide. Hopefully this helps you a little bit. The perpendicular bisector is perpendicular, so it has a right angle, bisects, cuts it into two congruent parts. Point of concurrency is called the circumcenter. And this theorem is that it's equidistant from the vertices of the triangle. So all these segments would be congruent. Next come angle bisector. It's going to bisect the angle, so it goes from the vertex to the opposite side, bisecting that angle. Point of concurrency is the incenter, and the incenter is equidistant from the sides of the triangle. So these have those little right angle marks. These are all going to be congruent. Then came the median. The median goes from the vertex to the midpoint of the opposite side, so it cuts it into two congruent parts. Its shortcut, or its name for the point of concurrency, is the centroid. And the centroid is 2/3 the distance from the vertex to the midpoint of the opposite side. So BR would be 2/3, RD would be 1/3, CR would be 2/3, R to the side would be 1/3, AR would be 2/3, R to the side would be 1/3. And lastly, altitude. Altitude goes from the vertex perpendicular to the opposite side. The point where they all meet is called the orthocenter. And there's nothing special here. It says the lines containing the altitudes of the triangle are concurrent. That just means they meet. There's no special theorem. Remember that the circumcenter is in, on, out, and it happens at the right triangle. It happens at the midpoint of the hypotenuse. The in-center is always in. The centroid is always in. The orthocenter is in, on, out, and on, or on the right triangle, it happens at the right angle. So this is basically everything we just covered in a nutshell. This is a really important slide. If you want to screenshot it, we will rewrite this. We will refill this in together. But you definitely want to make sure you know everything on this slide so that you can then apply it.